So in this last video, covering chi-square distributions and the goodness of fit test, we're going to take a look at some populations based on their percentages, and we're going to check to see if the population fits the given distribution. So this problem is definitely not a preference, no preference, because you can see that we're going to talk about three groups that are not all the same by default. According to firearms statistics, deaths for those fewer than 19 years of age are the following: 74% accidental, 16% homicide, and 10% suicide. Now these percentages indicate that this is not a preference, no preference test. This is a test where we are checking to see if the actual data matches the percentage. So this is the quintessential goodness of fit test. So in this sample, we did observe some accidental deaths, homicides, and suicides. Now, step 0 is very important here because we have to make a table since they didn't provide one for us. The table should have a row for observed, and it should have a row for expected. Across the top, we should have our categories, and I'll abbreviate them ACC, HOM, and SUI. We should also have a total table. That total will be very useful when we come to making our expected values down here. So, according to the data that we observed, there were 204 and 81 and 15 for the first three columns. Now, it's important to get the sum. Now, if we add these together, so we basically put the 96 together with the 204, adding these three would make a total of 300. So this is how many people were measured in this study. So what we would expect is we would expect 74% of the 300 for accidental, and 16% of 300 here, and 10% of 300 here. So to get these numbers, we take our percentages and turn them into a decimal, and then multiply them by the number of people in this study. So 74 times, or 0.74 times 300 is 222. So this is our expected value right here that we're going to use in list 2, as we use our observed in list 1. So we're going to continue this. 16% of 300 is 48, and 10% of 300 is 30. So let's compare the observed versus expected. The observed, these two are pretty close together, but the second column is pretty far apart, and so is the third column. So if we compare the numbers in yellow to the numbers in green, are these numbers too far apart to basically state that these percentages in the actual problem were okay? So that's where our null and alternative hypothesis come into play. Our null hypothesis, realizing that this is a goodness of fit test and it's not a test that is dealing with a preference or no preference, this null hypothesis is saying the population fits the given distribution of gun statistics. I'll just abbreviate that, stats. So that's the null hypothesis. The null hypothesis is always going to say the population fits the given distribution, or fits the data. Whereas the alternative is going to say it doesn't. So the population does not fit the given distribution of gun statistics. Yep, so the null hypothesis says the percentages are fine. The alternative hypothesis says these differences in green are too far off. So what's nice about this is this example is that there's just not a lot to it. I mean, there's only 3 columns, and the 3 columns are going to be easy to tabulate with an older calculator. So we take our observed minus our expected, and I could have done this in step 0, but I just can do it down here too as well. And then we divide that by the expected plus the observed minus the expected divided by the expected. And then finally, for the last column, the observed minus the expected divided by the expected. So I'm going to get my calculator out and go and take a look and see what this gives me. Okay, so get to a nice clear screen here, and I make sure my calculator is in classic mode. So if I push up to the mode key, if I click mode, I should be able to find that there is a classic mode on these newer calculators. Sometimes it's right there when you hit the mode button, the classic option's right there at the top. Hit second mode to get out of this, and now we're going to use parentheses, 204 minus 222 squared divided by 222 plus, use the parenthesis key again, 81 minus 48. And see, this is why I like classic mode, because you can see everything on the screen at once. Divided by 48 plus, one more to go here, 15 minus 30, parenthesis, square it up, and divide by 30. Now I'm just going to double check and make sure I have all of the expected values where they should go. Okay, I hit enter, and my x, or chi-square, score is pretty big. This chi-square score is 31.65. So if we have an older calculator, we have to use the chi-squared CDF. And that chi-squared CDF is on our graphing calculator under the second VARS option. Our lower number will be 31.65. Our upper number is going to be 10 to the 99th power. And our degrees of freedom is going to be the number of categories minus 1. So it's always one fewer than the number of terms I have listed here in option 1, so 3 minus 1 is 2. Some of you might think that the degrees of freedom is 299, and that's not true. We're actually not caring about the number of people that we've got in the study. We care about the categories of the percentages. So that is going to be our n, the number of categories. So the degrees of freedom is 2. So it's time to get out the calculator and see what that gives us here. So bring the calculator back, and now what we have is second VARS. And we're going to scroll down to chi-squared CDF, which is option 8 on my calculator. And it looks like my lower limit is going to be changed to 31.65. My upper limit is still infinity, or 10 to the 99th power, or 1 with 99 zeros on it. And the degrees of freedom in this case is 2. Go down to paste, and there's the formula right there. And the calculator will do the work and give me my p-value, which is not 1.34%. That is 1.3 times 10 to the negative 7 power. This is an exponentially small number. And what's important about this number is we have to move this decimal here 7 spaces to the left. So it's a decimal point and 6 zeros in front of that decimal. So that decimal is 0.1234561 So again, that 1.3, so just to kind of help you one more time, the 1.3 e negative 7, we move that decimal 7 spaces to the left, which gives us 6 zeros, 0.13. I've had other teachers say it's 7 zeros to the left if you put the decimal after the first zero. So however you want to learn it, you just can't leave exponential numbers like an exponential number. You got to write it as a decimal. That way you can compare it to alpha. And I don't really care what your alpha is. Your alpha is going to be bigger than that. Now you'll notice in this problem there wasn't an alpha given. There was no alpha given. And in those situations when there are no alphas given, you are going to assume the alpha of 5%. So if your alpha is 5%, then this is definitely less than alpha. And since, let's just move on to the evaluation here, since your p-value is much less than 5%, so since your p-value is less than alpha, we, W-H-E, why did I put a H there? That's silly. Come on, get rid of my mistake. We have sufficient evidence to reject the null hypothesis. Yep, those statistics those percentages are not good enough. We should not have had that huge discrepancy in the second and third columns. Now, if we want the calculator to do all the work for us, well, lucky for us, if you have a newer calculator, you have the goodness of fit test. So you can put your 204 in list 1, as well as your 81 and 15. And then in list 2, this is kind of what we wanted. We wanted our 222, we wanted our 48, and we wanted our 30. Okay, so there's our list 1 and list 2. And I'll show you this on the calculator. Hit the stat button. Let me move over a little bit. Let's hit the stat button and let's hit enter. And if I go up to the top and hit clear, enter, up to the top and hit clear, enter, that'll get rid of everything in my lists. So 204, 81, and 15. Move over to the list 2, 222, 48, and 30. Okay, so now I'm going to go stat. I'm going to move over to tests. I'm going to scroll down a bit until I get to the chi-squared goodness of fit test. Make sure it's the GOF test. And then I hit enter, and it looks like I got my list 1 and list 2 all set up, but my degrees of freedom is 2. 2 degrees of freedom. And then we're going to calculate here, and in doing so, you get my same 1.3 e negative 7, my chi-squared number, you see 31.65 right there, and also my degrees of freedom. So what's great about this is this this checks my work right here. So if you're worried about, like, if this is a test question or something and you want to check your work, you can always do it by hand. It doesn't take a long time. And then, you know, put stuff in list 1 and list 2 and get your answer. So that's pretty great. That is pretty great. Okay, so there we go. We've evaluated that. So now it's time to get to our last problem here. And this would be a good problem to maybe pause the video and see if you can try it yourself. We've got 2 tables that has observed number of pets students have in their homes matched to the expected percentages. Let's see if we can see if these percentages are correct at the 10% significance level. Okay, so if you try this on your own, in step 0, our big concern is to figure out where's the observed, where's the expected. Well, this is the observed vertical column right here. So what we have to do is we have to figure out the expected, and we'll put that off to the side here. Let me spell that correctly, you know, instead of what I just was trying to write. Okay, so we got observed and expected. So what I'm going to do is I'm going to take each percentage here and multiply it by a total, but we got to figure out the total first. Okay, so if we take the 210, the 240, the 320, the 140, and the 90, get a total of 1,000. Okay, now I'm going to take that 1,000 and multiply it by 0.18. So 1,000 times 0.18, and that gives me 180. And I'm going to continue that pattern. 1,000 times 0.25. And that is going to give me 250. 1,000 times 0.30, because I can turn all these percents again into decimals if I'd wanted to. Okay? Like 0.30, and 1,000 times 0.30 is 300. 1,000 times 0.18 is again 180. And 1,000 times this would be, careful on this one, 0.09. It's not 90%, it's 9%, which would get you 90 people. So if you added up all of these 5 numbers do add up to 1,000 as well. So this frequency is your list 1. And this over here is your list 2. So the first step here is the null and alternative. And again, we're evaluating these percentages, the percentages of number of pets these students have. And of course, the null hypothesis is going to say everything's fine, everything's fine. The population fits the given distribution of pet statistics. So pet stats. And of course, the alternative is saying it's not. So the population does not fit the given distribution of pet statistics. So let's do some calculation now. To do the calculation, we're going to take each category and subtract the observed minus the expected, divided by the expected. And here's the second one. We're going to take the observed, 240 minus 250 squared, divided by 250. And we're going to do the third one, 320 minus 300 squared, divided by 300. And again, you're always dividing by your expected. It's easy to make a mistake when you go observed minus expected. Sometimes you accidentally subtract by the observed, or you leave the square off, or some other silly mistake. Now, I think most of you are going to decide to do the option 2 here, but if you don't have that option, or the homework forces you to do option 1, you're going to have to be able to do it. Hey, fun thing about this last one, this 90 minus 90 squared divided by 90. 90 minus 90, according to order of operations, we do the inside parentheses first. That would be 0. 0 squared is 0, and 0 divided by 90 is 0. So really, we only have 4 of these to do. So this last one here doesn't really count. But if you do all 4 of those, I will tell you that I've done this problem several times. The answer is 15.622. So this is your test score. This is your chi-squared right here, your chi-squared test value, which becomes your lower value, 15.622, when you type this into the calculator. The upper value is going to be 10 to the 99th power, because chi-squared tests are most universally right tail. And then the degrees of freedom is going to be the number of categories minus 1. So that's going to be 4. We had 4 different categories. We had the 0, the 1, the 2, the 3, and the 4 plus, for a total of 5 categories of groups that could have, or groups of numbers of pets in their family. So it's time to get the calculator out and see what we get here. So let's get the calculator out. Let's move it over just a tad. Okay, and now let's turn it on. Go to second vars. Scroll on down to chi-squared CDF. Hit enter. Okay, my lower number here is 15.622. The upper limit is infinity, or 10 to the 99th power. Degrees of freedom is 4. We hit paste, and we get a very, very, very small number here. Okay, so 0.00357. 0.00357. So let me copy that down. My p-value is 0.00357. And then what I'm going to do is I'm going to go do the traditional goodness of fit test by plugging in my list 1, which is 210, 240, 320, 140, 90, and then on the other side, 180, 250, 300, 180, and 90. Okay, I will show you this on the calculator as well, so let's move this over a little bit. And let's go to Stat Enter. Now I'm going to clear these out by hitting Clear Enter. Now because this data set was longer, I could have just typed over these 3 data pieces with my 5 per column. That would have been fine. Alright, but, you know, sometimes it helps with a blank slate. Alright, looking good. Look at those 5 numbers there. Okay, move to the next column. 180, 250, 300, 180, and then finally 90. Okay, there we go. I got list 1 and list 2 in there, and now I'm going to go stat, move over to the tests, and I'm going to scroll on down until I get to chi-squared goodness of fit test. Make sure you use the goodness of fit test and not the chi-squared test. That's for the next series of videos, when we test for independence and test homogeneity. Alright, so we got our list 1, list 2 is observed and expected. My degrees of freedom is 4, and I'm going to calculate. And lo and behold, that's exactly what I got before by putting all 4 of these terms squared, observed minus expected squared divided by expected. And I also got my p-value exactly the way I needed it. Well, this is great. But now I had to basically, for the first time, I was given an alpha that wasn't 5%. I was given an alpha that was 10%. Well, shoot. Take a look at that. P versus alpha. Man, P is much smaller than alpha. So since P is smaller than alpha, we have sufficient evidence. we have sufficient evidence to reject the null hypothesis. All right, thank you for watching hopefully all 4 of my videos here, chronicling the introduction to chi-square distribution with a focus on the goodness of fit test. Thank you for watching.